All right.
Should smile more. Oh, the mic's on.
So, what we're going to talk about is building the fastest, most secure internet possible. And these two guys claim that it's much closer than we think, so we're going to try and drag that out of them. Rescorla is a fellow at Mozilla, and his sort of rival and friend is Jana Iyengar at Google. So these guys both work on different browsers, but as we're going to see, in order to make the internet work more quickly and more securely, it requires a lot of cooperation between different players. So what I was going to ask you guys is, one of the things that's happened is the internet seems to be going encrypted. Why, and why now?
Why? It should have happened a long time ago. I think there's been a lot of movement in trying to make content encrypted, and QUIC is pushing further towards making even transport information encrypted and so on. Not sure why. I don't know how to answer why now.
I mean, I think it's become clear over the past 5-10 years that there are a lot of bad actors on the internet, and that they would like to look at, tamper with, et cetera, screw with your traffic. And as people have realized that, they've realized that encryption is the answer to fixing that, and they started to roll it out. The other thing that's happened is that the technology has made it much easier, so things are much faster, and encryption is much cheaper comparative to other compute power. And there's also been this sort of, I call it a coalition of the willing, an effort across a number of companies, Google, Mozilla, CloudFlare, Cisco, Akamai, a pile of us, just to bring encryption everywhere. And so we started to systematically tear down all the barriers to rolling out encryption, everything from getting certificates to performance to latency. And as we do that, it becomes more viable and therefore more imperative.
The performance thing is quite interesting, right? Because one of the traditional objections to using encryption for anything was it's going to be slower, and we were at the same time trying to drive the web to be much faster. That seems to not be true anymore. What's happened?
Two things. So the first is, as I said, computers have just gotten much faster, and cryptographic algorithms have gotten much faster. So elliptic curve cryptography is much faster than old cryptography. AES is much faster than triple DES. So it chews up less compute power, and comparatively, it's a much smaller slice of what your computer needs to do. Obviously, that doesn't make the speed of light any faster, and round-trip latency, what used to be a big issue. But again, there's been this systematic effort over the past few years to remove as many round trips as possible from the protocols, so that we're getting to the point now where encryption doesn't require any more round trips than non-encryption, and that's what's happening with both QUIC and TLS 1.3.
So it's just for the audience to understand that, you just said something which is quite technical, which is right that it requires no more round trips. So just what was happening with TLS, SSL, so secure connections, and what's happened now?
Sure. So pretty much all encryption channel protocols involve a setup phase of a handshake where you send packets back and forth to establish the cryptographic keys that you use to encrypt the traffic. And so that involves overhead in terms of round trips back and forth between the client and the server before you can start sending any data at all. What people have realized over the past few years is that it's possible to, once you sort of have an initial context and you've ever had any contact with a server, you can save state, and you can use that to start sending data right away encrypted, just in the place where you would have sent data if it weren't encrypted. And so that's something, as I say, it's sort of an old idea, but it's been evolved in QUIC and TLS 1.3, and so now people are just starting to do that. And so that means that there's initial setup, like with the first time you contact Google, but after that, from then on, you can just go immediately.
So this is TLS 1.3. This is the new version of the confusingly named protocol SSL, which is sometimes called TLS because of history. So that's got a lot faster. But Jana, you're working on something which fundamentally rips up a lot of things that are there, right? So the internet as it's built today is built on layers, and those layers have allowed the internet to scale in a very successful manner because each layer is unaware, essentially, of the layer below it. So I've got TCP, which allows me to communicate between two machines, and along comes somebody who wants to build HTTP, who happens to be in the audience, and says, okay, I've got TCP, and now I can just put this protocol on top. Now, you've done something completely opposite, which is to say, but that introduces some problems, that independence of the layers. So tell us about QUIC. What are you trying to do with this consolidation?
Indeed. So, so I can start with just briefly describing what QUIC is. So QUIC is a super fast completely encrypted transport that we're building at Google for replacing the stack, as you mentioned, of TCP, TLS, HTTP2 on top of it. And what we get for it is we are able to eliminate a lot of the inefficiencies in the layering. So you have round trip times. For example, just one example, we were talking about round trip times earlier. TCP has its handshake round trip, and then there's TLS, which does its handshake. If you want to eliminate those round trips, you have to eliminate them in both layers. And they're independent layers, as you pointed out earlier, which means there are different players involved, there are different vendors who are shipping these products. So you have to ship it out in various different places, and you have to get the stack to do the right thing completely. So that's one sort of set of inefficiencies. With QUIC, we are able to establish a zero round trip connection, which is secure because it has equivalent security to TLS 1.3 in terms of establishing the connection in zero round trip. And we get that with one protocol. So making changes to this means that what we are trying to do here is pull in everything that you need to deliver HTTP content and turn that into one protocol so that whatever we need to do to optimize for web, for HTTP, we can do with this one protocol and make it work for HTTP instead of having to change multiple things down the stack.
Now, this is not an experimental thing. This has actually been shipped by Google, right?
Indeed. It's actually deployed now quite widely. And if any of you have either gone to a Google service today, including YouTube, on your desktop, you probably used, well, using Chrome, you probably used QUIC. If you used your Android device to go to a Google service using one of several apps or Chrome or YouTube app, you probably used QUIC. So yes, it's deployed quite widely. If you're using any of these things I just described, there's about an 80 to 90% chance that you're using QUIC.
And what's the experience been with rolling out? Because now you've thrown away half the layers of the internet. How is that operating? So you're obviously relying on some other layers that still are in existence, right, in order to get the packets there.
So QUIC runs on top of UDP. It replaces the functions of TCP, TLS, and the HTTP2 layer on top, but it runs on top of UDP. So operators see this as an increase in UDP-based traffic on the networks, but they can't look into the headers because it's fully encrypted. So they can't really make sense of what's going on inside the packets and the transport, which is very much by design. And we've been talking to operators constantly. We make sure that they are informed about the increase that they're about to see in UDP traffic. And I'd say that for the most part, people have welcomed this change. We are now about to kick off a standardization effort at the IETF, where there are multiple players coming in. Akamai has gone public saying that they have now adopted, they're working towards deploying QUIC. And there is a lot of interest in the industry because everybody wants to see this happen. This is generally just goodness because it's more secure and it's faster. Yeah.
And my understanding is it's faster in some of the most difficult environments. So we talked this morning with Ilya Grigorek about, long latency mobile networks and things like this. Why does QUIC have an advantage in that environment?
So there are a few reasons why, and difficult environments, I'll add one more to that, which is we've talked about developing regions and bringing internet connectivity to the next billion or the next few billion. And that connectivity is usually pretty crappy. It's over 2G or fairly poor networks. And QUIC is, by being a transport that is not embedded in the operating system, it's basically, we've built it as something that's embedded it's in user space. And it allows for us to ship changes to the client, make changes to the server, and not have to rely on devices in the network to change. Now, this is a fundamental difference from TCP, where the TCP/Y format was visible in the network, and there are a lot of network devices which do not allow TCP to evolve further beyond what it currently does because they have a certain presumption of what TCP means. Because the entire packet is encrypted in QUIC, devices cannot see inside them, only the endpoints see, so we can rapidly change the transport at both ends. This allows us to experiment and to deploy new mechanisms to adapt to whatever conditions we see. And we are able to deploy changes that basically are betterments to congestion control, to loss recovery and other transport mechanisms, betterments over TCP, and we're able to deploy them rapidly to all of these places as well.
you mentioned in what you were talking about there, the fact that it's entirely encrypted and operators cannot look inside the packets.
Yes.
Eric, we were talking last night about sort of this dirty little secret of the world, right? Which are these things that people call middle boxes, which are devices that have been looking at our internet traffic for a long time and sometimes modifying it. And it's not intelligence agencies, it's all sorts of other people. Should we talk a little bit about that as we open the box of this secret?
Sure. I mean, there are essentially anybody who's on path between you and someone else tends to look at your traffic, and they do it for all sorts of reasons. They do it for congestion management. They do it for traffic prioritization. They do it for security, antivirus, et cetera, stuff like that. Hotels and airports do it so they can get in the middle and show you their stupid captive portal. Carriers often do it so they can figure out what kind of advertisements maybe they should be showing you.
Right.
And so this happens all up and down the layers. It happens at the transport layer, as Jana was indicating, which makes it hard to roll out new kinds of transports. It happens at the HTTP layer, which makes it hard to roll out new kinds of things in HTTP. And then it happens sort of at the application layer, like the conceptual application layer above HTTP, where they do things like shove a captive portal in your face. And so and sometimes this is done passively, and they just look at things, and sometimes it's done actively where they shove things in. And so one of the things that in general we're trying to do is make that as difficult as possible, at least for people with whom you have no relationship at all. So there'll still be enterprises who think they need to get into the data that their own users do, and that's not something I think anybody who works in this field is particularly happy with, but we recognize it's kind of a reality. But at the very least, we want to be able to set up a situation where when I talk to Google or I talk to CloudFlare, that the network I'm on that I have no relationship with except that they're providing me wireless, that they can't do anything about traffic.
For example, it's quite common for school districts to have boxes which do filtering, and in order to do that, they have to deal with the encryption that's
right. So generally enterprises and schools and people like that, they think they own the endpoints, or at least they own the network and they're restrictive. And what they'll do is they'll require that the endpoints be configured to allow them to inspect. And there's a variety of ways of doing it, but the typical way is they impose a new certificate on the endpoint that allows them to man in the middle of the traffic. And as I said, this isn't something that anybody who kind of works in this field is particularly thrilled about, but we recognize it's a reality, and the technology we're talking about doesn't change that scenario, but it makes it much easier to differentiate between people who you call legitimate inspection devices versus illegitimate inspection devices.
I'm assuming there are also some downsides of this. One of the ways in which the internet's got a lot faster is by doing caching. And it's quite common in mobile networks to actually cache. If everyone's looking at the New York Times, well, let's just cache that without telling anybody we're caching it. What's the effect, do you think, of this rollout of encryption going to be on that sort of thing?
Can I take this?
Yeah, I mean, obviously, this makes the kind of caching impossible. The data is actually quite equivocal on how much that caching helps. We spent some time trying to, in IETF, trying to figure that out. I think, over maybe 2-3 years ago, we started realizing this was the trend, and we started trying to figure out, do we still need caching, and if we do need it, what are we going to do about it? And there's some interesting work going on in what's called blind caching, about how to do encrypted caches that don't allow traffic inspection, but still allow caching. That's very preliminary work, and as I say, there's still an open issue about whether or not this is actually an advantage. In many cases, I think there are two things. In many cases, the operators who do these kinds of things either claim that they have an advantage for users, but in fact they don't, and maybe they know that, maybe they don't. And in many cases, they had an advantage for users 10 years ago, but the environment has changed and now they don't. As more and more websites get dynamic, caching, that kind of caching, and CDNs become more proper, that kind of caching becomes less valuable.
I'll add that this is a very interesting tension, I think, and there's definitely a lot of conversations happening in this space right now about how to cache with encryption. But this really shouldn't be they should not be at odds with each other. Arguably, the premise should be that whatever we are doing, including caching, should respect the security properties that we want. So I think that's where we want to get.
Let's just dial forward a bit. So QUIC starts an IETF process. People like us and others roll it out. It suddenly becomes the dominant protocol. One of the things that's interesting is that having sort of torn up the foundations of TCP and TLS and HTTP2, you have a chance to keep changing.
Right.
So do you think QUIC becomes ossified like TCP has, or do you think there's some sort of evolution possible?
The hope certainly is that there will be evolution. QUIC has as one of its premises evolvability, meaning that it gets us in two ways. One way is by making it a user-space protocol. We no longer rely on operating system updates to various operating systems to get shipped. This can be shipped as a user space library, and you can get automatic updates in user space, and that's much faster than waiting for other system updates. Second, by being entirely encrypted, the transport mechanisms can evolve without having to worry about middle box interference or middle boxes basically falling over because they had expected a certain particular behavior of transport. So in both of these ways, the mechanisms are there to allow for QUIC to keep evolving. As we go through the IETF process, again, the plan is to retain that evolvability in the protocol and to allow for distributed experimentation with it. So yeah, that's certainly the hope.
I mean, I think so far we're seeing, you know, when these protocols were being designed 20 years ago, I think we didn't actually have a great idea how to build things evolvably. So A, you had to worry about these kind of inspection endpoints, which we're trying to get past with encryption. And B, if you look at, say, you know, a number of the pieces of TLS that were intended to be evolvable, we found aren't as evolvable as they were, and we have to sort of fight with that. And I think now we're learning how to build systems that do a better job in the face of endpoints not evolving as well as you'd hope. And I think you see this in QUIC, where QUIC sort of started out with being incredibly monolithic and with its own custom crypto, and we're evolving that to use TLS 1.3 instead, and we see that that's actually that's working quite well. And that's because I think the people who designed it had a good idea of how to build systems that could plug and play different pieces as they needed to. So I hope that in 10 years, we won't be having to fight with, oh, I want to roll out a new feature in QUIC or in TLS, and then 2% of endpoints blow up when I try to give it that.
Right. That's certainly my hope as well.
I wanted to touch on the difference between HTTP2 and QUIC, because HTTP2 is now out there, being widely deployed, and you know, much of the promise of HTTP2 was that it would give us high performance for websites, that improved over HTTP 1.1, and it was also rolled out fully encrypted as well. So what's the step up that QUIC is going to give us that we haven't got with HTTP2?
There's just directly there are two steps up, or two separate steps. One of them is that with the HTTP2 stack, you have HTTP2, TLS, and then TCP below it. You get all the beautiful multiplexing and everything else that you get in HTTP2, but then you serialize everything and shove them down one single serialized TCP connection, one single byte stream. With QUIC, we are able to eliminate the delays that can happen, head-of-line blocking delays that can happen in TCP, because we maintain the parallelism across trees, within a connection all the way through to the other endpoint, even at the transport level. The second step up is, again, as I was pointing out earlier, the fact that TCP connections can be terminated in the network, that people can step on TCP connections. For example, do things like limit the receive window to limit a connection's throughput. Things like that cannot be done in QUIC, fundamentally just because the transport headers are encrypted. And those are, I think of them as two separate steps up. In addition, QUIC has also sort of has this notion of a connection that is divorced from the standard typical 5-tuple that we have for TCP, which allows it to do things like multipath and use multiple network interfaces at the same time. This allows us to do things like, if you're familiar with MPTCP or multipath TCP, like that, just off the bat.
So do you think in a 5G environment we might be sending packets over multiple cell towers as well using something like QUIC?
If they are exposed to the endpoint, if the interfaces are exposed to the endpoint, then yes, certainly we could be doing that.
So, Eric,
I just want to bring out one point that Jana just made. So as we roll out H2, what we're seeing, we absolutely see performance improvements, but what we see is in aversive network conditions, they mean things with a lot of loss, the multiplexing starts to really break down because I've had a line blocking. And so one of the huge advantages of a transport that isn't stuffed on top of TCP is that it'll be much more resistant and degrade much more gracefully as the network starts to degrade, which is incredibly important in these developing nation environments and in mobile environments.
And we've actually seen evidence of that. We've seen QUIC really sustain itself through high loss environments in remarkable ways. And it's definitely helpful that we're able to build new fast recovery, loss recovery mechanisms based on what we've learned in the past.
I think it's worth just describing for the audience a little bit what this head-of-line blocking problem is, right? So,
Sure.
So if you could, let me see if my microphone works, this won't work. If we think about in the TCP environment, what's great about it is it guarantees delivery of data. And it does that, so if something gets lost, it will retry, and it comes in order as well. How does that generate a problem? It sounds great.
So that sounds fantastic, except the ordering requirement may be too stringent for applications that don't completely require that. Specifically, HTTP is an application that has when a client speaks to a server and is downloading data, it's usually multiple objects, and there is no ordering requirement across these objects. You may want to receive one object, all the bytes from one object in order, but not necessarily have the objects themselves ordered. So if there's a loss of a packet that contains data from one object, delivery of a subsequent object also gets blocked at the client because TCP doesn't know that these are two different things. It thinks of this as one single byte stream. QUIC allows you to have multiple streams within one connection. So when there is a loss in the network of a packet that contains data from stream 1, say, data that's being received over stream 2 within the same connection will get delivered to the application. So that basically avoids subsequent objects from being blocked behind an object that cannot be delivered right now, because QUIC has an understanding of the structure within the set of requests that are going out.
Great, and Eric, I wanted to touch on TLS 1.3. Why have we done 1.3, and what's better than 1.2? Right,
so it turns out I'm always appalled to realize I've been banging away on this SSL TLS stuff for like 20 years now. So when SSL was first designed 20 plus years ago, we didn't actually understand that much. The people did it, were very smart, but didn't understand as much of it as we do now about designing protocols. And so some mistakes were made, and also when people thought performance, they really thought about CPU performance. They didn't think about latency, because latency was not the dominant cost of running any kind of encrypted connection. And so what's happened is computers have gotten much faster, but the speed of light hasn't gotten any faster, and unfortunately we haven't figured out how to do anything about that. So round-trip latency has become much more important. And at the same time, there's been a bunch of security problems with SSL and TLS that were they're sort of baked in from the beginning, but nobody sort of understood how to deal with at the time, or didn't really understand how methodology to find. And so things have gotten much better. And so it sort of became clear about 4 or 5 years ago that it was time to do something, a really substantial revision. And so we started looking at both the best sort of academic practice on how to build secure protocols and the best ideas people had about how to make fast protocols and try to put them together into one protocol. And at the same time, Google started working on QUIC, and so we took some inspiration from there as well as some other pieces of work. And so the idea is to build sort of the most modern, low latency cryptographic protocol we know how to build and deploy it to as much of the web as we possibly can. And it was really fortuitous, I think, that QUIC has been developed at the same time, so we're able to sort of bring those efforts together.
Yeah, there was experience with this, and so we could certainly share that experience and learn from it.
What I think is exciting about this is that there's no compromise here in terms of speed or security. We're going to have both of those things. That's going to be the default. When do you think it's going to be socially unacceptable to visit a website that's not encrypted?
Isn't it already? It should be if it's not.
I mean, I think Chrome is making an effort to warn people, that you're visiting, one of these old-fashioned HTTP websites.
I think we're a ways away. Our telemetry shows that we're getting to roughly about 50% of HTTP hits or HTTP pages are encrypted. 65–70% of transactions are encrypted because of things like Gmail and Facebook, which are all encrypted and do a lot of back and forth, even though it's only one page. So we're quite a ways from 100%. I think what we'd like to see is a situation where it's embarrassing for you to roll new property that does anything substantial isn't encrypted. And I think one thing that we try to say as security people is, you may think you don't need encryption, but you really do, and it's just hard to think about a threat model where you don't have it. I sort of wanted to caveat something I said earlier, which is this is a huge effort to build something this new, and we're going to have made some mistakes. So don't think that we've solved all security problems for all time. We're just trying to clean up the swamp and make things as best as we can do now.
Yeah, and we I think we are learning what it means to do zero RTT and security with zero RTT, and we're going to trip along the way. We have to be able to pick ourselves up. I want to come back to just one thing you said earlier, which is the question about TLS and making it unacceptable. I think that companies like CloudFlare play a very important role here, because making it unacceptable for origin servers to actually have HTTP, I think that can be done if we have a number of people, and many of them might be in this room, in fact, make it unacceptable for origin servers to serve that.
Okay, great. Well, we've used up our time. I know it's flown by because it's fascinating, but we do have a time for questions from the audience. So are there questions?
Tim.
I think there's a microphone somewhere.
So one of the most frustrating aspects of the net can be the captive portal, which blocks your computer and blocks all the programs which normally run on it. When you happen to walk through a part of an airport, you say, and encryption will make it difficult for those captive portals to actually find a way in to get you to click on the box and open up that. How is progress on protocols to do the right thing? Is the best practice for if you want to do the right thing in your airport, what should you do, and how is that coming along?
Yeah, that's something we've not made as progress on as we were hoping to. The unfortunate situation appears to be that the captive portal vendors are not actually interested in cooperating with browsers or operating systems in allowing us to detect captive portals. So all the operating systems, or at least the Apple operating system, I believe Microsoft as well, and Android, had detection of captive portals. What they do is they go back to some site they know is intact and they try to talk to it. And sometimes that works, and sometimes the vendors actually explicitly whitelist just those sites, so that then when you try to go to New York Times, then they can show you the captive portal. And the reason they do this is that they want to force you out of the restricted sandbox that the operating system puts you in for the captive portal and into the full browser environment. So I think that the people who make the endpoints, I know we at Mozilla would be very happy to have a standard that could advertise to us you have a captive portal, and then we could talk to you. We've not had much uptake from the people who make them, but I would invite that conversation.
Yeah, there's certainly a need in the space. It'd be good to get those captive portal folks in the room. That tends to be hard to do.
So there's another question over there.
Hi. So I think I appreciate encrypting everything all the time. I don't know. I'm sort of on the fence about that for just a whole lot of reasons. But regardless, what I'm interested in hearing about is the root of trust and certificate authority specifically. So if we encrypt everything but we don't do a good job with certificate authorities, what have we actually accomplished? So were there any thought around what the next version of CAs might look like?
Well, so first of all, I want to say that I think people overrate how bad the situation is with respect to the web PKI. There have been a few high-profile breaches, but by and large, the situation is actually pretty good in terms of misissuance. That isn't to say that things are anything like perfect or anything like what we'd like to have, but I don't think it's as bad as people seem to let on. There have been a number of efforts along these lines. They sort of all, again, it's sort of not nothing's a complete solution, but they're pieces of solutions. So on the on the client side and the side of self-help, we have things like pinning, HPKP, or HSTS, which is sort of a halfway solution for people. To stop people that partly stops people from accepting totally bogus certificates. And on the systematic side, we have efforts like certificate transparency. So I think when you put those together, we're coming closer to a solution. Probably there's some more iterations to really know what to do and have a perfect answer. One thing I do want to say is any authentication system is going to have misissuances. That you just cannot be authenticating billions of people and not have fraud. And this is a risk management issue about containment. It's not an issue about perfect security.
Okay, well, thank you so much for coming and talking to us about these things. It's great to hear from people who are really rebuilding the guts of the internet to make this stuff work. Jana, Eric, cheers.